Hi everyone, let's start. So today we are going to do two things. So first we will finish the part of algebraic independence. Some of this we saw today, so it will be easier, I hope. And then we will give a concrete example of the simplest function field, the rational function field, and explore what are its places. So far we learned about various ways to think about a point abstract in an abstract way, like valuation ring, maximal ideal, the place. So now we will actually see an example what are all these look like in a concrete example. So let's start with the definition. So okay, so K and L are fields. L contains K as a subfield. So subset S of L is algebraically independent over K if what? Independent. So
there's no polynomial with the
right. So if for all in S1 to Sn in S and N non-zero polynomial K 1 to Sn, we have what? This. Independent, then it's not zero. So it is algebraically dependent if we can find n elements in the distinct element in S and a non-zero polynomial with coefficient in K, such that once we substitute S1 to Sn in P, we get 0. So with the examples, so if L is K xy, so the rational function is in two variables, x and y, then what can you say about this set? Right, this is obviously algebraically independent of K, but we consider x plus 1 and x squared. Then what? And which, right, what is the polynomial that demonstrates this fact?
1 square 2 x.
Okay, so for example, you can take x1 minus 1 squared minus x. So once we substitute x plus 1 minus 1 is x squared minus x squared. So it's a non-zero polynomial. So these two satisfy the polynomial relation. Okay, so we will claim that A will be algebraically independent Okay. So maybe I can already say so. If an algebraically independent set which is maximal with respect to inclusion is called the transcendental basis of L over K. And now suppose we have an algebraically independent set which is not necessarily maximal. So how can we check if it is maximal? So the claim says that a element of L, then S union of S and A is still no longer algebraically dependent, depend on the so L over K algebraic over K S algebraically independent. Let's try to add a new element A. This will be algebraically dependent if and only if the element A is algebraic over Ks. So the proof. So this direction is in the problem set. So I hope you saw the message of the first problem set is on the website. So this is the last question. So let's show this one. So suppose that this is algebraically dependent, then what can we say? Thing S1 S and a non-zero polynomial P in K x1 to xy plus 1 because we want those and A such that P s1 to xn A is 0. So we satisfy some non-trivial polynomial relation. Then I write x1 to xn plus 1. Okay, so in order to show that A is algebraic over S, we want to find the polynomial with coefficients here, that A is the root of this polynomial. So it makes sense to write it P like this. I transform 0 to B. Some polynomial in the x1 to xn times x1 to I. So it's just a polynomial in xn plus 1 and coefficient in these polynomials in the first variables. Now what can we say with, of course, with PD? PD non-zero, so the highest, this is the then what can we say? So, well, we know that P is 1 to Sn A 0, and it's so first things that we can infer that B must be positive. Why? If D is 0, then there's only P0, and that's all. And P0 is non-zero, and then what is the contradiction? Right, because S is algebraically independent, so P0 of S1 to Sn cannot be 0. So D is positive, and what is our P of A? P of A will be D. S1 to Sn X to the I. So this is a polynomial in Ks X. So check that this polynomial, the univariate polynomial with coefficients, which are in fact polynomials in S1 to Sn, is a non-zero polynomial in this ring, and A is a root of this. So this shows that PA non-zero, PA of A is PA of A is 0, so A is algebraic. Okay. Clear? Okay. So a useful corollary, then we started today with yield, so S algebraically independent, then if S is algebraically independent, then S is maximal algebraically independent, or in other words, is okay. I write both, so is a maximal algebraic independent, also called transcendental cases, if and only if the extension L over K S is algebraic. Right, so it's immediate, right? Because if S is maximal, then why is this algebraic extension? Well, take any L here, any A in L, then S union A is no longer algebraically independent, it's algebraic dependent. So A must be algebraic over Ks. So it's one line and similar this direction. And this is really useful because now, okay, so you can use just like in linear algebra arguments of existence of a basis and any two bases have the same cardinality. So the same way, any such S can be completed to a maximal algebraically independent set, which is a transcendental basis. So a transcendental basis always exists, and any two such have the same cardinality. And this cardinality is called the transcendent degree of the extension L over K. So he'll just mention all of this today. So what is the bottom line? So if L over K is any field extension, then we can start with K. We can find S a transcendental basis of L over K. So Ks is what is called purely transcendental extension. This just means that S is a transcendental basis of L over K. And then we can take L, and this is algebraic. So any field extension, we can break it to the purely transcendental part and the algebraic. So example, the case of a function field, which we define today, is just what? It's a field extension. So we have f over k is a function field. If we have the field k, okay, function field is always an algebraic function field in one variable in this recitation. So it has a transcendence degree 1. So just take x, which is, there exists x in f, which is not in k, that is transcendental. So kx, in fact, the field of rational functions in variable x, and then take some, and then f is fine. In particular, algebraic. Okay, so again, the function field is just a field extension such that the transcendence degree of f over k is 1. So we can take x, which is in f, transcendental over k, and then we have kx, this purely transcendental extension. And then f is just a finite extension of this. So, and one more thing, we insisted that, so this was the condition that f over kx finite. And we also insisted that k, the field of constants, all the elements here which are algebraic over k are in k. So in other words, that just means that every element which is not in k is not algebraic over k. So every element in f which is not in k is transcendental over k. But for now, let's consider the simplest function field, which is the rational function field. Questions?
So just to make sure I understand, like these are the conditions that every function field can be thought of as k of x, f,
Right.
where the expression is finite.
So every function field f over k. So we have the base field k. We have an x in f, which is transcendental over k. So we get the this field, which is a k that extends k, and then we take a finite extension of this one, and we insist that this thing. So every element in f which is not in k is also finite.
Every element in f that is using k.
So for example, you can then take f, which is kx, when we have an element y such that this relation. So in this case, we extend the field of rational function kx by adding an element y, which is algebraic of degree 2. So this is a field extension of kx degree. But let's keep it simple. So now we will only discuss this where f is kx.
Just make you understand. So if there will be two variables, so it's kxy, right? And x and y are transcendental. Because that now you define like one variable.
Two variables.
Yeah.
So
the k and f for x.
So right. So the transcendental basis will contain two elements, x and y, which are algebraically independent.
Yeah, and this will be
Like
and this will be a
x
finite.
and y are not algebraically independent. Y is algebraic over k.
Yeah. And like f will be a finite extension over this k.
Right.
Okay.
So now we consider the simplest case. So we have a field k, and we consider the rational function field. So what are the elements? So the rational function field is just the field of rational functions, or if you want, take the polynomial ring kx and then take its fraction field. So the elements here are quotients of polynomials up to the equivalence relation of the fraction field, right? Like x over x squared is the same as 1 over x. Since we can multiply diagonally. So, okay. And we can check that, well, okay, it is indeed a function field since it is the transcendence degree of kx over k is 1. X is a transcendental basis. F over kx is finite because f is kx, 1. And The only thing that is not trivial is to check that indeed every element in Kx, which is algebraic over K, is in K. So this is not trivial, and it's an exercise to show it.
Again, like K prime, just to make sure, like every element in F, which is some.
Yeah, so let's take some rational function. If it is a root of some polynomial with coefficients in K, then it must be a constant. So the elements of K prime.
Every object in F is
K
was in K.
It's all the elements alpha in F, such that alpha is algebraic over K. Alpha is the root of some polynomials with coefficients in K.
Yeah, okay. So alpha is like like depends on K or something like that. Like alpha can be generated from K or something like that. From K.
It's algebraic over K.
Yeah, okay.
Like, yeah, so if you take 6 over R, then it's not good because the element I is in 6, and it is algebraic over R, the root of x squared plus 1, polynomial with coefficients in R, but it's not in R. So
yeah, so this is not this doesn't K prime doesn't equal.
Yeah, so we need to change it to 6 over C, and now every element which is algebraic over C is already in C. So the elements here, which are not here, are transcendental.
So it's like the field is correct. Is okay.
Right. The field of constants indeed contains all the constants. Okay. Okay, so let me remind you. So now we only focus on this function field, and we want to find its places. So what is a place? So in general, let me remind you, a place is just a map from a field F to a field L with the infinity symbol, such that what? So think of it as F are the elements of F are the functions that we want to evaluate, and the output is the value. The place evaluates the function. So the constant function 1, its value is, so a place is an abstraction of a point. So every point, one way to think of it is just give me a function and tell me what is the value of this function at this point. So the constant function 1, its value is 1. If we have sum of A and B, then the value of the sum is the sum of the values. Same for product, unless we are of the edge cases of the case that the image is infinity, like A and B have poles, so only when it is defined. Okay, so questions about this. And we say that the place is trivial if it's never sends to infinity. So in other words, the image of F is contained in L.
So what do you think about it is trivial? Like in which sense is trivial? You can evaluate every point, but why is it trivial?
It will be clear maybe. So this was in general a place, and now we want to define a place of a function field. So what is it? Is a place of a function field. So it's a place from the field F to some field L and infinity. That is trivial on K. So, right, so, and of course it's not trivial. So a non-trivial place that is trivial on the constant. So how should we think about it? So for intuition, you can think these are the functions in the function field, the elements of the function field, which are functions. And phi is a point, a place, and phi tells you, give me a function, and I will tell you what is the value of this function at the point. So, and if the function is not defined, then it has a fault, then return infinity. And the fact that we insist that the place is trivial on K, it just means that if you give me a constant function from K, then don't tell me that it's not defined at the point. All the constant functions are defined. Don't, right? If you take a function in K, then phi of A is not in K. And this should follow. So, okay. So now F is Kx, and we ask ourselves what are the places, the points of the places. Oh, so one more comment. So how can we think about it? So let's illustrate. Okay, so we have F, we have K. So there are the constant functions, there are the elements of F which are not in K, which are transcendental over K. We have the map phi, which maps to L and the point infinity. So let's see. So the place should be trivial on K. So K, the elements here cannot be mapped to infinity, so they are mapped to L. So this is phi of K. So in fact, phi is a field homomorphism from the field K to the field L. And if you remember, a field ring homomorphism between fields is always injective. So phi of K is isomorphic to K. So, right, so it's not necessarily surjective, but if we replace it with phi of K, the image, then it is injective and surjective. So K and phi K are isomorphic. So we identify them. So we will, without loss of generality, think of phi of K just as K. And we will think that phi maps each is the identity on K. So every element of K is mapped to itself under this identification. Good. And L in particular, if this is, think of this as K is a subfield of L. So we are looking for a places of the function field phi from Kx to L in this set. And we can assume without loss of generality that every element in K is mapped to itself, and L is a field extension of K. Right? It contains then a copy of K, which we think of as K. Okay, and what else do we want? So we want the place to be non-trivial. So we want that some function in F will be mapped to this. And the other are mapped to so some to this and some to this. Okay. So this is this is F bar. So the image of F well, all right, so what is F bar? It's the image of F minus infinity. Okay, so hopefully this is clear. So the constants are mapped to themselves, the identity. There is some functions that are mapped to infinity. The other functions that are not mapped to infinity, and the functions that are mapped to f bar are the valuation ring, the functions that are defined on the point. So this is the relation between the valuation ring, the subset of f, the subring of f, that its image is f bar, not infinity, the functions that are defined on the point. Okay. Questions?
So understand in which sense triviality means like a pole. Like why functions with no poles like why places with no poles are non-trivial? Trivial, I mean. Like in my head, like having a pole is just annoying. It doesn't make you non-trivial. It makes you.
Oh, good. We will see it, I think, next week. It will be more. Okay. Okay, so let's see which places, what are the possible places. So how to begin? So again, so far we know that we identified phi of k with k, and we know that k is mapped. Phi, the restriction of phi k is the identity. But what is how phi acts on the points in f which are not in k? So what can we do? Let me just replace it to kt because in the notes I use kt, it's the same. Different. Okay. So T is a transcendental basis of the function field. It's a transcendental element, so it lies here. So let's ask ourselves, what is the image of T? So case one, the image of T is finite. Okay. So one option is that T is mapped to some element of L, which is not infinity. Then what can we say? Then if I give you a polynomial in T, an element, if f is in kt, what can we say about phi of f? Right, it's also in L, right? Because it's homomorphism. So that is L, right? It's just phi of some polynomial in T should be a polynomial with coefficients in K. So we assume that is some that AI is mapped to itself and phi of T. And phi of T is in L, so everything here is in L. So consider the restriction of the place to the polynomial ring. Then we get that every polynomial returns a value. In fact, we get a ring homomorphism. Right, all the polynomials are the values of all the polynomials are in M. Okay, and now what? What can we say about?
Maps to zero. I mean.
Right. So what is the kernel of this? Okay, so the kernel is always an ideal, and remember, if L is a field, what can we say about this? not just an ideal, but fine. Right? Remember, because since if we take fg in the kernel, then phi of fg is 0. So phi f times phi g is 0. So phi f is 0 or phi g is 0 because this is the field. There are no zero demands. So f is in the kernel or g is in the kernel. So it is prime. And then what? So we know what are the prime ideas of the polynomial rings over the field. So one option, the kernel is trivial, 0. Second, the kernel is what? Generated, okay, KT is a PID, so every ideal is generated by one polynomial, but prime ideal, what is its generator? Right, for a unique, monic, reducible. Okay. Good, so
Again, give something for TFS P0 is like, what is P0? Like, you like.
So we began with some phi, a place of the function of the rational function field, and now instead of taking we restrict the domain only to the polynomials.
On the polynomial with the brackets. Okay, you know.
Right.
Okay.
Polynomials, and then the image of each polynomial is in L. So we get a ring homomorphism from KT to L. And the kernel is a prime ideal, so it's either 0 or the ideal generated by P, where P is some unique monic reducible polynomial.
This is because the prime ideas of polynomial rings are something we know.
This form.
Yeah.
Okay, so in case 1, well, I leave it to check. It's in the notes. Check that if the kernel is trivial, then for every element in the function field, we have the value of phi of this element is this thing. So there is something to check here, but at least it's well defined since right, if this is a rational function, then g is non-zero. So g is non-zero. So phi 0 of g is not 0, because if the kernel is trivial, then the only thing that is mapped to 0 is 0. So if g is non-zero, then phi 0 of g is non-zero. So it is well defined, and it is an element in L. So you can check using these properties that indeed, if the kernel is trivial, then phi of f over g must be of this form, which is in L. And then what's the problem? But it should be non-trivial. We want that some function will have a pole. We want that there will be some element in KT that is not defined at this point, that it is mapped to infinity. So this case is not good. So this is the good case. So okay. So now suppose that the kernel is generated by P for some monic irreducible P. Then what can we say? So let's write tau for the value of p. We know that it's something in L, say tau. Then what is phi of p, the polynomial that generates the kernel? Right, so it is on the one end it's 0, on the other end it's, then phi is a ring homomorphism, and then you can check it is p of phi of p. Right, if you just, since it's a ring homomorphism, which is p of tau, which is 0 since p is in the kernel of phi. So the image of p is just a root of this p, which was irreducible in KT. And if we take a polynomial such that age is not in the ideal, or saying p does not divide age in KT. Okay, so obviously phi of p times any polynomial is 0, because this will be in the kernel. But if we take h, a polynomial which is not a multiple of p, then it's not in the kernel. And phi of h will be what? Again, h of phi of p, h of tau, and it's not in the kernel, so it must be in L and non-zero.
Why phi of p is equal to p of phi?
Here, just because they write it as a polynomial and then use the fact that phi is polynomial.
And then you say like p of t must be like, how do you think about this step? Like that if there's a single monomial.
Okay, so it's the preparation for the next step, so maybe now it will be clearer. So far, all we know that once we take a polynomial, the phi of p is 0, and if we take a polynomial which is not a multiple of p, then it's non-zero, some non-zero element of L. Now, what is if we have arbitrary function in the function field? Then we want to evaluate phi of u. That's our goal. Find what is phi of u for general u. So here's something that we have already solved. So we can write u as a quotient f1 over f2, and we can decompose f1 and f2 to irreducible factors. So let's take all the products of p out. So it's p to some power f over g. So simply take all the p from the numerator and all the powers of p from the denominator. So we get p to the m times f and g, where m is in z, and f and g of prime, and p is no longer divided f, and no longer divided g. Okay. So we can always do this. P is some specific polynomial. Take any rational function, take its decomposition to irreducible factors, take all the p's from here, all the p's from here, cancel. You will get with a unique m, such as p of m times f over g. Then what is p of u? So three cases. Well, first, if m is 0, this m. then what can we get? Then f and g are just polynomials that are not divisible by p. So if we take a polynomial which is not divisible by p, we get just the value of this polynomial once we substitute tau. So what would we get? We get this. If m is positive, then what will we get? 0, right? Because this will be 0. And if m is negative, then. So we already saw this place. So if p was take p an irreducible polynomial in kt, then any u you can write as a unique representation in this form, and then the phi is just this given by this, where tau is a root of p in some extension. Which extension? For example, kt modulo p, modulo the ideal generalizable. Okay, so what else can we say? So what is the, so let's call it phi of p, because it's for every p we get. What is the OP, the evaluation ring of this place? Remember, the evaluation ring is the subring of the field, which consists of all the functions that are defined, that are not mapped to infinity. So in other words, all the functions that are not here, so all the functions that when we write u as this form, then what m must satisfy? Right, so it's all the functions em times f over g, where m, so equivalently, this is just all the rational function f over g such that p does not divide them. So it does not divide g. If it does not divide it, then m is 0, and if it divides it, then m is 0. Anyway, it is defined. And so this is OP. And what is the valuation? Valuation, right? So for every element in KT, we want to say the valuation is the what is the order of the 0 or a pole this function has at this point. So it's just m. Since if it is 0, then this is some non-zero value. So the valuation is non-zero. If m is positive, then it has a 0 of multiplicity m. If m is negative, it has a pole of multiplicity minus. In particular, the valuation is discrete because the values of the order group is m is an integer. Okay. So this is almost all the places, and this is called the p-edit valuation.
We already proved what you wanted, right? You proved only when you said that there are some that are infinity.
Right.
Like you were in the middle of the proof, so that the proof ended like where P of Q can be infinity. Is where it ended, and now you're saying like extra properties of this valuation.
Oh, so this is actually, you can check that this is a field. So a place, sorry, this is a place. The corresponding valuation, it's called corresponding valuation ring is OP, which is this, and its corresponding valuation is this. So these are exactly all the places of the rational function fields KT, such that the element P is mapped to some finite element. So we find quite a lot of places, right? there is a one-to-one correspondence between the monic irreducible polynomials kt and the places of kt which maps t to some finite number. And this is the place, the corresponding place.
So what you showed, you're trying to show that there is non-trivial, like you try to show.
So okay, so we just find some of the places. So these are some possible places. So
Every polynomial like generates this kind of place in the
right. So every place of kt, if phi of t is not infinity, then it has to be of this form. So there is one more case. So there is, if you remember, there is one more place that is not of this form. And it is obtained when phi of t is. So we will see this next. Okay, so next time I'll try to repeat it and finish with the last place that is missing.